think this should work. Okay, this is pretty straightforward. I think anyway. Let's see. Oh, I see. That's a cute problem. Ah, shoot, okay, this A does not work. That's unfortunate. Oh, duh. Yeah, okay. That's unfortunate. Okay, so clearly we'll take all the non-negative ones. There might be a greedy solution here. Not sure if this is correct. Oh, well, it's not correct on samples anyway. Let's see. Oh, hold on. How does that decrease the answer further? What? Oh. There we go. Okay. Let's submit to the easy version first, I guess. Okay, so this doesn't work. I'll stress test this. Huh, okay. That's interesting. Okay, there we go. Oh, duh. Okay, that's unfortunate. I should have caught that earlier. Wait, let's see. let's see. Yeah, I had a greedy for the inversion counting part of the problem that I think is just wrong. But let's see if it works now. Okay. All right, cool. think I see how this works. There we go. Okay, cool. I think this works. That's actually a pretty cool problem. Huh, okay, that's interesting. It's a very weird lower bound on n. I guess it makes sense because it seems like there's not going to be enough information to determine the permutation when you have fewer numbers. Like with n equals 3, there's only one query you can do, and that doesn't help us very much. So it seems like if we can find 1 and 2, then we're done in n more queries. think I see how this works. Let's see. Let's see, hold on, there's one more detail I have to figure out. Okay. Yeah, I think I see how to do this. No problem. so because of the end limit, it's going to be a real pain to test on my end, so I'd better just test by submitting. Okay, let's see. Maybe I do need to just test on my end. Okay, so let's see. Okay, so it does seem to be guessing incorrectly. But at the same time, you can see it's identifying the position of the extreme values correctly, which is strange. Oh. Oh, I'm an idiot. Okay. Yeah, I just flipped. I'm printing the result where the second value is greater than the or first value rather than the other way around. Okay, wrong on pretest 2. Took a pretty long time to run, so now I'm wondering if it maybe takes more than 420 queries to get this to break. No, I don't think that can happen. Oh, let's see. I think I actually maybe need to be a little stricter here. Okay. Yeah, I see what went wrong. I would appreciate if my solution would run, but I'm a little concerned because I would be surprised if that got WA2 so quickly. Yeah, so there's something else going on. Maybe I'll try stress testing. Okay, well. Hold on. No, my interactor is just wrong. I don't think any of what I've just done fixes it, but I also am kind of curious if this gets RTE, because if so, then that'll tell me a lot about what the error is. Does this pass now? Okay, I legitimately do not know what I did to fix this. Kind of worried though, because this definitely seems like the type of problem where you could very easily just get WA on some pretty high test number, so we'll see how this goes. Sure, taking their sweet time judging this though. That's for sure. Alright, well this seems like it could take a while. Hey, accepted. What's my rank? Alright, third place. Looks like there's still some people who could who could pass me, but yeah, I'm pretty happy with that. I thought F was I actually thought all of these problems were really nice. This is definitely one of the higher quality Div 2 rounds that I think I've done lately. Yeah, I'm definitely very happy with how this went. Hopefully these guys don't pass me in the next couple of minutes. Anyway, maybe I will go ahead and do some solution explanations. So yeah, maybe I'll just, actually here, let me see how my friends are doing first. I'm curious. Cool. This guy just submit a compilation error or something. Alright, yeah, let's do some solution explanations. Some of these may not be especially complete because I solved several of the problems by essentially, I don't want to say guessing because there was some underlying intuition, but I sort of figured out what the what the solution was going to be without actually proving it. So for some of the problems, I will be asserting certain facts without proof. But yeah, let's go ahead and get into it. So, okay, first problem. We have two n distinct integers, and we want to rearrange them in a circle such that each integer is not equal to the arithmetic mean of its two neighbors. So the idea here is let's call the n smallest integers small numbers and the n largest integers large numbers. And the idea is that we're going to alternate between large numbers and small numbers. So, like, for example, if we represent a large number by an L and a small number by an S, we're going to do something like this. And the reason this works is that then every large number is going to be between two small numbers, and every small number is going to be between two large numbers. And we can pretty quickly see that there's no way for a large number to be the mean of two small numbers because the large number is greater than both of them. And likewise, a small number can't be the mean of two large numbers because it's smaller than both of them, and so it can't be their mean. Yeah, and so the way I do this in my implementation is I just sort the array, and I then essentially use elements 0 through n minus 1 as the small numbers and elements n through 2n minus 1 as the large numbers, and that leads to a pretty concise implementation. All right, cool. Problem B, we're given an integer x, and we want to create it using some number of integers that are formed only using the digit 1 with at least two 1s, so we can't just use 1 itself. All right, so I think the key observation here is to try working modulo 11. And the motivation for this is that as soon as we get to as soon as x is congruent to 0 mod 11, i.e. x is divisible by 11, we can just finish by using a bunch of 11s. And the key observation here is that if our number has an odd number of digits, it's going to be, or that is, if like a number that consists only of 1s with an odd number of 1s is going to be congruent to 1 mod 11, and a number with an even number of 1s is going to be 0 mod 11. So that is 11, 11, 11, 11, 11, 11, 11, etc. or 0 mod 11, and then 1, 1, 11, 1, 11, 11, etc. are going to be 1 mod 11. And we can prove this basically by using induction in that, like, so for example, 1111 is just equal to 11 times 100 plus 11, which we know is going to be congruent to 11 mod 11, which is 0 mod 11. And likewise for this one, like 111 is equal to 11, is going to be equal to 11 times 100 plus 1, which is 1 mod 11. But anyway, so then the basic idea is we want to get to a number, or we want to subtract out as few of the, or we want to basically see if we can get to a number that's 0 mod 11 before x becomes negative. And it can be shown that the most efficient way to do this is to just keep subtracting 111 until either x is 0 mod 11 or x is negative, at which point the answer is no. And the idea is that if x is big enough to subtract 11,111 even once, we're definitely going to be able to subtract 111 enough times to get it down to 0 mod 11. So if a solution exists, then there will always be a solution using 111. And so that brings me to my implementation, which is pretty concise. We just subtract out 111 while n is not evenly divisible by 11, and if n becomes negative during this process, then the answer is no. Otherwise, it's yes. All right, cool. So let's look at problem C. So we're given a line of n potions, each of which increases your health by a sub I, but a sub I can be negative, in which case the potion decreases your health. And so you want to consume as many potions as possible without making your health negative at any point in the process. This is a bit of a weird problem, just because the overall setup makes it seem like it's possibly going to be DP, but it turns out that that's not the case. And the main reason for that is it's pretty difficult to incorporate the amount of health you have into any sort of DP state, especially because a sub I can be so big. you can have a really huge amount of health at certain points in the process. And so it turns out that the solution here is a greedy approach, which I have not proven rigorously, but I think intuitively it makes a decent amount of sense. So the first observation is that clearly if a sub I is non-negative, then we should consume that potion because there's literally no downside. All it's going to do is it's going to help us consume more potions later in the process. So if a of I is greater than or equal to 0, then definitely we should just add it, or we should just add this potion to our answer. And now the harder case is when a potion harms us and we have to decide whether we want to take it or not. And what my solution does is it basically kind of maintains the optimal solution at each step of the process. So that means if the last potion we've taken, so H in my solution stores our current health. So if we can take this potion safely without dying, then I just say, okay, let's do it because that's going to let us increase our answer, and increasing our answer is good. Now the one problem is it might be possible that we take a potion that does that does a high amount of damage to us now that stops us from taking a potion that does less damage later on. And that's what the second case accounts for. So what my second case is saying is if there's a potion that we consumed earlier that dealt more damage than the potion we're trying to take now, then we should just not consume that potion and consume this one instead, because that's going to keep the number of potions we consume the same, but it's going to leave us with more health for the future. Okay, and so I don't have a proof that this is optimal. I think intuitively it makes some sense in that it seems like, so clearly if we can immediately increase the number of potions we take without taking any fewer earlier, then we should, and otherwise we should only take a new potion if we can do so while improving our overall health and only removing one other potion from the set. But that's not particularly rigorous reasoning, and so but I felt confident enough in it that I decided to ultimately just code it up and submit. All right, so let's look at D. For D, the key observation that I made, which I also don't have a proof of, although I don't think the proof is terribly difficult, is that basically here I should read the problem first. So we have a string containing only the letters A, N, T, and O, and we want to rearrange them such that essentially the distance to get back to the original string using only swaps is as high as possible. And a helpful fact that I think is pretty well known is that essentially the number of the number of swaps that need to be made is equivalent to the number of inversions in the array. And the number of inversions is the number of pairs of elements. Here, let me. So basically the number of pairs of elements I, j, such that element I appears before j in the original array, but I needs to appear after j in the modified array. Okay, so the key observation here is that the optimal answer is always going to involve putting all the A's in one block and all the N's in one block and all the T's in one block and all the O's in one block. And so the only meaningful decision we have to make is in which order to arrange the blocks. So for example, in the first test case, we have to figure out that the N should go before the O, which should go before the T, which should go before the A. But it's a given that the two N's are going to be placed together. I don't have a proof of this yet. I think that I've seen a decent number of problems like this, and so it was a pretty quick observation. I'm guessing that the editorial will contain a proof, so if you're curious, take a look there. But anyway, so as far as how to implement the solution, essentially what I do here is I iterate over every permutation of the 4 letters after I map the 4 letters to 0, 1, 2, and 3 to make them easier to process. And then the rest of this code, essentially, it builds the answer string corresponding to this permutation, and then this inner loop counts the inversions. Let's see. So the idea for this inversion counting code is in this chunk here. I essentially count the number of characters that have appeared already in our potential answer string, that haven't appeared yet in our potential answer string. So they're going to appear later in our answer, but they appear earlier in S, and so those are going to contribute to our contribute to our inversion count. If you haven't seen inversion counting before, I would encourage you to look it up and do a practice problem. I'm kind of glossing over my code here because it's relatively standard. But and so afterwards I take the maximum of I set the answer to be the largest possible the inversion count, and I print out the corresponding string. All right, so let's look at E. So we're given a suffix array of up to 200,000 characters with an alphabet consisting of up to 200,000 characters, and we have to count the number of strings that produce the given suffix array. So this is a nice combinatorics problem. So the first observation is clearly for example, the string at in this first sample case, for example, the string at position the character at position 0 has to be less than or equal to the character at position 2, which itself has to be less than or equal to the character at position 1. Because, like, for example, if character 0 is greater than character 2, then 0 would come after 2 in the suffix array. So in general, the character S sub I must be less than or equal to the character S sub I plus 1. But that's not the only restriction we have, because in particular, sometimes the equality case won't be valid. So for example, in this first sample case, we're not allowed to have character 2 be equal to character 1, because actually, hold on, let me make sure that I might be mixing this up. I'm kind of just remembering back to when I did this problem originally. Let me check real quick. Okay, no, sorry. We can't have character 0 equal to character 2. And that's because if character 0 were equal to character 2, then character 2, or then the string beginning at character 2, which includes only character 2, would then be a prefix of the string beginning at character 0, and so 2 would appear before 0. So basically, I guess this is just kind of an example, but basically what I'm implying here is that the only thing we need to worry about is whether S sub I can be equal to S sub I plus 1. And so that's the only thing we need to determine, and then we sort of have and then we've sort of figured out the structure of how the ordering of the strings has to work. So the idea here, so the way we do this is basically first of all, as I just sort of explained, if S sub I plus 1 is equal to n minus 1, then no, because S sub I minus 1 is going to be a prefix of, because then that string is going to be a prefix of the other one. And likewise, if S sub I is equal to n minus 1, then yes, they can be equal, because in that case, S sub I will be a prefix of S sub I plus 1. And then otherwise, the observation is that basically if, so let's say, then otherwise S sub I, if character S sub I is equal to character S sub I plus 1, then string S sub I is a prefix, it appears earlier than string S sub I plus 1, if and only if string S sub I plus 1 appears earlier than string S sub I plus 1. And the intuition here is essentially that if we have two strings beginning with if we have two strings beginning with the same character and one comes before the other, then the string beginning with the second, or then the string here, let me explain this with an example. So let's say we have the string, I don't know, the strings ABD and ABE, EF, let's say. Then we know if we want to compare these two strings, we first compare their first character, the A's, and if they're the same, then we compare their second character. And we know then that ABD comes before ABEF if and only if BD comes before BEF. And so that tells us whether we can, and so that gives us a criterion we can use to tell us whether equality is allowed, whether S sub I can be the same character as S sub I plus 1. Because we know whether the string beginning with, because we know whether the string beginning with S sub I plus 1 appears earlier than the string S sub I plus 1 plus 1, because we have it in our array. Okay, so let me walk through my solution real quick. So I first read in the input, and I identify the position of each character. And then here, this line essentially implements the criteria that I wrote up in here. So I first check if either of these is equal to n minus 1, and otherwise I see if S sub I plus 1 appears after S sub I plus 1 plus 1. And this essentially identifies the case where equality is not allowed. And so then I count the number of cases in which equality is not allowed, and the rest of this is essentially a combinatorics problem. And so so I'm not going to go into too many details. This is an idea that's commonly referred to as stars and bars if you haven't seen it before. But essentially the idea is that we need to, or the way I model this is that we need to move from one character to the next k minus 1 times. And we can move in n plus 1 locations, because we can sort of increase the character either between any two strings, we can increase the character either between any two positions. We can increase it before the first position, and that essentially is equivalent to making the first character something other than character 1, or we can increase it after the last character, which is essentially equivalent to making the last character something other than character k. And moreover, we have CNT or count positions where we're not allowed, or where equality is not allowed. Moreover, in CNT positions, we must increase the character at least once. And so the idea here is then we have k minus 1 minus count increases that we are free to place, and we have n plus 1 locations to put them. And it's a well-known theorem of combinatorics that if we have A items to place in B positions, there are A plus B minus 1 choose B minus 1 ways to place them. And so that means that our answer is n plus 1 plus k minus 1 minus CNT minus 1, or alternatively n plus k minus count minus 1 choose n plus 1 minus 1, or just n. And so that gives us our answer. And of course, I just get the choose function by implementing my combinatorics template. All right, so that's E. And so then finally, we have F. This is a tricky interactive problem. So I think, first of all, it's helpful in this sort of problem to think about like what sort of information will help you, or like at what point is it easy to figure out the answer. And here what I sort of settled upon is that it would be really helpful to know either the position of 1 and the position of 2, or the position of n and the position of n minus 1. And the reason is, so let's say we know where 1 is and we know where 2 is. Then if we query if the values of our query are 1, 2, and x, then our three differences are going to be 1 for between 1 and 2, x minus 1 between x and 1, and x minus 2. And we know 1 is going to be less than x minus 2, which is less than x minus 1. And so that means that our result here is just going to be x minus 2. And so what that means is that if we can query the position of 1, the position of 2, and another position that we don't know, we can take the result and add 2, and that gives us the value at that position. And so that means that if we have 1 and 2, we can identify the remaining elements in about n queries. Okay, and so that means that so similar logic works for n and n minus 1. In that, like, if we query n minus 1 x, then our distances are 1 n minus x and n minus 1 minus x, and so the median's n minus 1 minus x, and we get the same result. Okay, so that means we want to identify either 1 and 2 or n and n minus 1. And so the tricky part, the part that took me about half an hour of thinking to figure out, is to figure out how we do that. And so here's the solution I eventually settled on. The first thing I do is I just make queries completely at random until I find one that gives me a relatively small answer. I restrict it to be less than or equal to n over 8. And so now let's say so we know that query of a, b, c is less than or equal to n over 8. And so what that means is, essentially, so let's say that these values are x, y, and z in increasing order. So x is less than or equal to y is less than or equal to z. So then the differences are going to be y minus x, z minus y, and z minus x. And we can see that z minus x is going to be the largest of these things. So the query is going to give max of y minus x or z minus y. And moreover, since z minus x is equal to y minus x plus z minus y, we know z minus x is less than twice our query. And so what this tells us is that if the result when we query is less than or equal to n over 8, then the distance between any two of our elements, like for example the absolute value of if we say our permutation at A and our permutation at B, is going to be less than or equal to n over 4. Because we know this value is either going to be y minus x, z minus y, or z minus x, and the largest of these is z minus x, which is less than twice this. Okay, so now we found two elements and we know that they're pretty close together. How does that help us? The way it helps us is that it lets us query our first of all it lets us find either 1 or n, and the way we can do this is, so let's say is basically, so for example, if we query 1 p of a and p of b, then our results are going to be absolute value p of a minus p of b, p of a minus 1, and p of b minus 1. And we can prove using some some inequality facts that either this result is going to be greater than, or is going to be we can prove that either let me explain this differently. So basically, we can prove using some facts about inequalities that among the queries of the form x, a, and b, the maximum value will occur exactly once when x equals 1, or when the value at x is equal to 1, or the value at x is equal to n. And a proof of this will probably be in the editorial, but the gist of it, this is why we need the condition that that a and b are pretty close together, because otherwise this doesn't work out. Yeah, unfortunately that's a pretty hand-wavy explanation. The proof is pretty long, and so it's going to be difficult to go over via audio. I may write up a version of it and post it at some point later, to provide a text explanation. But anyway, so that lets us identify either the position of 1 or n. But then moreover, the other fact that we can prove is that there will be, and so let's say this maximum value is k, then the value k minus 1 will occur in this list at most twice. And one of those positions, if we have, like, let's say we have p of x equals 1, then one of those positions will be the location of 2. Or actually here, let me rewrite this. If it occurs once and p of x equals 1, then this is the position of 2. Otherwise, it is the position of n. Or if p of x equals n, then it's the position of n minus 1. So in this case, we're done because we have 1 and 2 are n and n minus 1. Otherwise, the two positions are just 2 and n minus 1. And so then we need to figure out which one is 2 and which one is n minus 1. And the way we do this is, so let's say, for example, or yes, we need to figure out which one is adjacent to our, to whichever of 1 and n we know. So that is, if we have 1, we want to find 2, and if we have n, we want to find n minus 1. So I'm going to explain the case where we have 1 and we want to find 2 because the other one is identical. Basically, like, let's just pick some random element in the middle of our array. So, and if we query 1, 2, x, then as before, we get x minus, actually, I guess I already used x. So if we query 1, 2, let's say some value v, then we get v minus 2 as we said before. Whereas if we query 1, v, n minus 1, then assuming v is between 1 and n minus 1, which is the case as long as v is not equal to n, then we get, so our values are v minus 1, n minus 1 minus v, and n minus 2. And we know n minus 2 is going to be the largest, so we get max of v minus 1, n minus 1 minus v, which is greater than or equal to v minus 1, which is greater than v minus 2. And so what that means is that the value is that where the smaller query is going to be the one that includes 2, and the larger query is going to be the one that includes n minus 1. And so let me walk through my code real quick. This is where I randomly generate queries until I find a sufficiently small result. This here is where I perform essentially all of these queries. And so then I find the highest result, that's cap. And then the position that gives the highest result, I say, okay, that's the position of 1 or n, and I just call it 1 here. And then otherwise, if the value is 1 lower than the cap, then I say, okay, this is the potential candidate to be the position of 2. And so then I say, okay, if there are 2 possible candidates, then this line here addresses the case where our third element is actually n. But then basically I say, okay, whichever has the smaller query result is equal to, or is the position of 2, or the position of n minus 1, as the case may be. And so from here, so I initially assume, so you may have noticed by now that we know either 1 and 2 or n and n minus 1, but we don't know which is which. So this is where our condition that p of 1 is less than p of 2 comes in. Because at this point, I query every element, and that lets me figure out the answer, assuming that we're in the 1 and 2 case. But then, if I'm in the n and n minus 1 case, then essentially what's happened is I've inverted all of my elements. So like 1 should be n, 2 should be n minus 1, 3 should be n minus 2, and so on. And the way I can tell if this is the case, if I'm inverted, is if my answer is the first element of my answer is greater than the second element, because in that case I violated this known condition that p of 1 is less than p of 2. And so in that case, then I just flip my answer and then I output it. So yeah, I think this was a pretty nice problem. Overall, I think this is actually a really nice problem set. So it was a fun contest. This one, obviously doing a full explanation is a little difficult, so this is more just a summary of all of my steps. But a full solution will be posted in the editorial with proofs of these facts about inequalities that I used. So I would encourage you to check it out if you're looking for more details. I should note, by the way, for some, I should probably explain an analysis of like how many queries this is going to use. So clearly this step here where I query all of the x, a, b is going to use about n queries. And likewise, when I end up finding the answer in this loop, I use n queries approximately. And so that means that I have about 420 queries left to handle this step, to start querying random things until I find a sufficiently small one. And it can be shown that the probability that I don't end up finding a sufficiently small value in that many queries is really low. Let's see, I haven't done the precise math, but I want to say that it's bounded below by roughly 1 in 64. I think, or sorry, 1 in 64 is like the probability that I end up with a correct result is at least 1 in 64. And so the probability that that doesn't end up working for 420 queries is about 1 in 1,000. I don't think that's a particularly strict bound, though, I want to say. So, yeah, so I think it should work pretty consistently. But, yeah, so I think that's the contest. Let's see if I ended up in third place or if someone passed me. Come on. Let's see. Did CF just crash? That's fun. I'll just give it a minute longer. Wonder if M2 is up still. Can't check my standings on there, but... Alright, well, let's see. I guess I don't want to keep waiting forever, so I will go ahead and stop the video, and I guess you'll know what rank I eventually got because it will probably be in the title. Yeah, thanks for watching.